Today we're diving into a landmark paper from Google's quantum AI team that could genuinely change the future of computing. It tackles the single biggest obstacle to building a functional quantum computer, and you know what? The solution is completely counterintuitive.
Just think about that for a second. It sounds completely backward, right? And pretty much everything we build, from our cars to our phones, adding more parts just means adding more ways for things to go wrong. But in the wonderfully bizarre world of quantum mechanics, that very idea might just be the key to unlocking everything.
And that's not just a theory anymore. For the very first time, researchers have actually proven it works. They built a larger, more complex quantum system and showed that it was more reliable than its smaller cousin. So to really get why this is such a mind-blowing breakthrough, we need to understand the huge hurdle all quantum computers have to overcome.
And that brings us right to the heart of the problem, to what I like to call the quantum contradiction.
See, the building blocks of these machines are called physical qubits. They're the little guys that hold all the quantum information, and they are astonishingly powerful. But, and this is a big but, they have a fatal flaw. They are incredibly fragile. The tiniest vibration, the slightest shift in temperature, what physicists just call noise, can completely wreck the calculation.
So, just how bad is this problem? Well, right now, even the best quantum processors make an error roughly every 1,000 operations. And that might not sound too terrible, but for the kinds of problems we actually want to solve, designing new medicines, creating new materials, we need billions of operations to run flawlessly. We are not even close.
So how in the world do you build a reliable computer from parts that are fundamentally unreliable? Well, the answer is this brilliant concept called quantum error correction.
The idea is, instead of trying to build one single perfect physical qubit, which might be impossible, you create something called a logical qubit. You take one piece of quantum information and you spread it out. You encode it across many physical qubits. They all work together like a team, constantly checking up on each other to find and fix errors before they can derail the whole thing.
Honestly, the best way to wrap your head around this is with an analogy. Think of a physical qubit as a single, fragile thread of cotton. It snaps really easily. But a logical qubit, that's like a thick, strong rope woven from hundreds of those threads. Even if one or two threads happen to break, the rope itself holds strong. The information is kept safe.
Okay, but this brings us right back to that paradox we started with. If you're adding more threads, more physical qubits, aren't you also adding more potential points of failure? So the billion-dollar question has always been, is there a tipping point where adding more qubits actually helps you fix errors faster than new errors pop up? Does making the rope bigger really make it stronger? For years, this was all just a beautiful theory. But now, we finally have an experimental answer. So let's take a look inside the Google AI experiment that put this whole idea to the test. All right, so the researchers used an error-correcting method called the surface code. And it's really clever. It has two different types of qubits. You've got your data qubits, shown here in gold, and they're the ones that collectively store the protected information. Then you have the measure qubits in blue, and they act like tiny auditors. They're scattered all throughout the system, and their whole job is to constantly check on their neighbors for any sign of trouble. So what they did was set up a direct head-to-head comparison. On one side, they built what's called a distance 3 code. That's our smaller rope, using 17 physical qubits in total. And on the other side, a much larger distance 5 code, our bigger rope, using a whopping 49 physical qubits. The stage was set for a showdown, bigger versus smaller. Which one would be more reliable? This error-checking process just runs in these constant rapid cycles. The blue measure qubits interact with their neighbors, and then they're measured. That measurement tells you if the group's state is what you expect it to be. If that state suddenly flips from one cycle to the next, it's like an alarm bell goes off. An error has been detected. Then, a regular old classical computer looks at the pattern of all these alarms to figure out what went wrong and how to fix it. And the really cool part is, it does all of this without ever disturbing the protected quantum data itself. So, after running this whole experiment thousands of times, comparing the smaller code to the larger one over and over again, what did they find? Which rope was stronger? Well, the results were unmistakable. The smaller code, the d equals 3, 1, had a logical error rate of just over 3% per cycle. But the larger code? It came in just under that, at 2.9%. Now, I know, that doesn't sound like a huge leap, but it is a clear, statistically significant victory for the bigger system. For the very first time, scaling up actually led to fewer errors.
To put a number on it, that's a 4% relative reduction in errors. Think about that. For the first time ever, making a quantum error-correcting code bigger didn't just add more problems, it actually suppressed them. It worked.
As the authors themselves put it in the paper, this result illuminates the path forward. This isn't just another small step, it's the proof of concept that this entire weave a stronger rope strategy isn't just a clever idea, it's a practical, real-world roadmap.
So what does this milestone really mean for the future? Where does this path actually lead?
Well, it leads towards a critical goal in quantum computing known as the error threshold. You can think of this as the magic tipping point. If you can build your individual physical components, your threads, to be good enough to get their error rates below this threshold, then something amazing happens. Every time you make your logical qubit bigger, it doesn't just get a little bit better, it gets exponentially better.
This chart from the paper basically shows us where we are on that journey. This experiment is operating right here, in what they call the crossover regime, this yellow and green area. In this zone, making the code bigger helps a little bit, and that's exactly what they just proved. But the real goal, the promised land, is to improve the hardware enough to get us down here, into the blue and purple below threshold region. That's where making the system bigger gives you those massive, game-changing improvements.
So, what's stopping us from crossing that threshold right now? Well, the paper points to a few key culprits. It turns out most of the errors happen during those 2-qubit operations that create entanglement. Another big one is data qubits just losing their quantum state while they wait around. And then you've got these rare but really damaging events, like a stray cosmic ray hitting the chip, which can cause a whole cascade of errors that are way harder to clean up.
But here's the ultimate takeaway from all of this. For years, the path to a truly fault-tolerant quantum computer was, in a way, a matter of faith. It was a theory. But now, for the first time, we have hard, experimental proof that this path is the right one. The strategy isn't to build perfect parts, but to build good enough parts, and then simply scale them up, letting the system heal itself.
This experiment really is the first concrete step on that path, and it leaves us with a seriously exciting question. Now that we know the way forward is to scale up, how fast can we walk that path? And what incredible new frontiers are we going to unlock when we finally get there?